Good morning, students. Today we are going to discuss VLSI Design Unit 5. Okay, topic Design Strategies for Test. Okay, so in that we have to discuss Design for Testability. Design for Testability. Generally, it is called DFT. Okay, in VLSI, right? So in the previous class, we discussed about various test methodologies and we discussed fault models, right? Different type of fault models. Okay, so how to overcome these fault models? Okay, so that the concept is nothing but design for testability. Okay, so design for testability shows the fault model to test the chip in the manufacturing process. Okay, so let us write the comment here. DFT, I am writing design for testability shows the fault model to the to test the chip or dies, we can call, in manufacturing process. Manufacturing process. Okay, so DFT is nothing. It refers to these design techniques that makes test generation and application cost effective. Okay, so generally DFT refers test generation and we can call test application cost effective. Okay, so see here, the aspect of testing is based on basically uh, two methods. Okay, so you can call the aspect of testability ability is based on two concepts, you can say. Okay, so that are generally we can call controllability. One is controllability and second one is observability. Okay, so what do you mean by controllability and what do you mean by observability? Let us see. See, first one, controllability is nothing but, so the concept is I'm not discussing here at the circuit level. Okay, so how to reset 0 to 1, 1 to 0, the controllability, right? So I'm not discussing here, just a concept I'm giving here, right? So it is a measure of how easily any node mean input output node, okay, in the circuit can be controlled. Okay, so controlled how? By resetting or by setting, I can say, it to 0 or 1. Okay, through what? Through the primary inputs. Okay, so I will show how what is the primary inputs, the basic inputs which are giving, that is our primary inputs here. So next is observability. Observability. Observability what? It discuss about the state. Okay, present and next state. Okay, so I can say observability is the ability to observe either directly or indirectly, or indirectly, the state of any node in the circuit. Node in the circuit. Okay, so basically, so testability is basically based on these two concepts. One is controllability. Controllability means, see, in the faults we have generally outputs will be, suppose, for example, in the previous lecture I discussed the faults. So the faults generally, if I have an AND gate, for example, okay, and A B two nodes I have, the output is Y node. Okay, then here I have SA0 stuck at 0. Okay, so in this case, what observe controllability will, this it will be control input and output. Okay, by okay, by resetting 0 or 1. Okay, so for our convenience it is resetting 0 or 1. Okay, in this we have so many methods, testing methods we have. Okay, in that how to do that concept we will go through it. Okay, so this is a controllability. Observability means we need to check the state. Okay, which state it is actually. Okay, if circuit is suppose you have three more NAND gates, then which state, present state or previous state values will be calculated. Okay, of the circuit directly, that are directly or indirectly, the state will be, state of the node will be observes. Okay, which state it is actually, right? So let us how generally it has happened. See here, the model of circuits generally, circuits is nothing but sequential circuit or combinational circuit. Okay, basically sequential circuit. If I take this is combinational logic. Okay, then it consists of primary output and consists of primary input. This is the primary input, right? So when you have the memory devices, like say flip flop here, okay, so this concept, this is called next state, and here it is present state. Okay, Now these are the primary input and primary output. Okay, and in this combination, in this circuit, we have here, suppose for flip flop, we have a clock. Okay, so see, if we apply flip flop or memory device in the next stage, okay, it becomes present state. Okay, so in this fashion, observability will be observe the state of the circuit. Okay, and controllability will reset the fault values by setting 0 or 1. Okay, so based on these concepts, uh, testability will be took so many methods. Okay, it has so many methods. Right, so let us discuss DFT classification. Okay, so classification, uh, DFT, design for testability, classified into two types we have. Okay, so basically these are classified into two types. So in the above lecture, about topic observability and controllability, we have circuit level also how to observe, how to control. Okay, so I just briefly discussed on that to understand them. Okay, now the first one is in this. The first one is ad hack technique or methods, you can say. Okay, you can call methods also, techniques also. Second one is structured methods. Methods, or you can say techniques. Okay, so both this is also techniques, right? So these two testing methodologies we have in the design for testability. Okay, so in structured, basically we have so many. One is I can say BIST is nothing but built-in self-test. Self-test. Okay, another is general scan test. Another one is, you can say, partial scan, and we have boundary scan. Boundary scan, and we have IDDQ, which means what? VDD. Okay, quantities. This is one of the technique. So so many methods are there for testing. Okay, so as per our syllabus, we will discuss few in this case, right? So first one is, you will see attack. Attack technique or method. Okay, so as name suggested, okay, so basically this adapt technique is used for specific designs. Okay, so basically this one, see, if you are designing, you are testing one particular circuit or particular design. Okay, if it does not available structured techniques, then go with this. Okay, basically this technique is used for very small circuits, okay, in the industry. If structured techniques are available, then go directly with structured techniques, because adapt technique is used for specific designs only, not all designs, right? So I will write few points here. Okay, so adapt technique, as name suggested, what it do is to provide more tests and control pins or inputs. I can say pins, I will mention better. So we are making extra pins, control pins, okay, to test the given circuit. Okay, for example, if I go with one example, suppose this is my AND gate, this is another AND gate, and connected with OR gate. This is output Y, and A, B, C, D, R, C. These are the inputs which are we have test. Okay, we need to test. Okay, so input pattern. This is generally called input pattern or test inputs. Okay, so this is test inputs. Right. Okay. So in this case, for example, I have fault here. In the last class, I discussed. Okay, and naming it Z. Okay, this is fault. For example, right? So we need to add more. It provides more tests and control pins. Okay, so what I need to do to overcome this, okay, this fault, we need to add extra pin. I named it E. Okay, so this is control pin. I need to control from here. Okay, and test will be increases A, B, C, D, E. Got my point? So these type of specific uh, designs, okay, we can use adapt technique. Okay, so this is nothing but a control pin, okay, which added extra to overcome this fault at the output level. Okay, right. Second point, if I want to say second, let us see is point 2. So insert multiplexers. Okay, insert multiplexer in order to increase the number of internal nodes means pins here, that can be control the external node. That is all. Okay, sorry, external nodes, right? See, one example I would like to give here also. How will the design support for the same circuit? If I give same circuit OR gate with these are the input. In this case, we need to insert a multiplexer or add a multiplexer. Okay, see here, this is mux. Okay, in this case, anyway, 2 into 1 or 4 into 2, whatever that, 4 into 1 mux. Okay, 2 into 1 mux in this case. So what we will do, suppose I have a fault here, this is my fault, then we need to add connection to mux, and this control pin take as another. Okay, so this is a control test. We need to control test this one, right? So this is external node, I can say. Okay, so see, then we have a output like this. We need to overcome this given faults. Okay, so in the adapt technique, okay, we are using 2 points. One is, see, one is to provide more tests. Okay, input more tests and control pins. We need to add external control pins here also same, and we need to insert muxes. Okay, to control the test pattern, okay, input test pattern, right, to get the proper output to overcome the faults, okay. What are the types of different types of faults, okay, right. Next we will see structured technique, second one, okay, classification of DFT. In DFT, the second one, uh, structured technique or method, you can say, okay. Let us go with it. So in this, generally we will see the first one, built in self test, BIST. See, built in self test, okay. So in this case, uh, we can go with any design circuit, okay. Wherever you want to test the circuit, you can do it, okay, with the BIST, okay. So see, BIST, the basic structure will be, if you want the structure, how it will operate basically, okay, we have test pattern generation, generally it is called TPG, okay. In the bracket I'm writing here, right. Next one is, we have circuit under test, okay. So CUT it is generally called, okay. So these two are, after completion of test pattern generation, then it will move, next stage is circuit under test. Then after this one we have TRA, okay, test response analysis, okay. So this is generally called TRA, okay. Now to control these all, we have a controller, okay. So I will write separately like a block. So this is I can say controller or control unit, okay. So this is connected to both, right, okay. So this is the basic structure of the BIST, I mean built-in self-test, okay, generally it is called BIST, okay, structure of BIST, this one. So which means what, for a control unit, if general words, if I take in another fashion, this is say logic based control unit, then this will be taken as test pattern generation, and we have, after this we have CUT, circuit under test, that's nothing but CUT, right. So next one is the response, okay. So test the response, test response analysis, okay. So this is TRA, okay. right? So we need to go for given circuit, generate the test pattern generation. Then next stage is see, here also we have number of different component in between like mux and gates. Okay, next is circuit under a test. Okay, next one finally is we need to go for test response. Okay, right. Next is next we will see test pattern. Okay, and this is also classified into three types. First one in BIST test generation. So I'm discussing here briefly. Okay, see test pattern generation. We have the first one. This is also classified into three types. Okay, so we have three types here. The first one is exhaustive testing, and the second one is you can say pseudo exhaustive testing. Okay, and the third one is random testing, that is pseudo random testing. Okay, now the first one is exhaustive testing. See, in the exhaustive testing, let us I will write here the first one. Okay, in the exhaustive testing, what will happen for a given any circuit? Okay, all possible inputs will be provided for the next stage. Okay, as simple as that. Okay, suppose if I have a circuit like and with one OR gate, any circuit one of them, and this input will be like this. This is to I have A, B, C, D are the inputs. Okay, this is suppose say Z, Y. Okay, this suppose this is my design circuit. Okay, in this case, if I take A, B, C, D, then what are the now we need to test exhaustive test. Okay, all see exhaustive meaning itself. Okay, generally it represents all possible combinations basically, right? So 0 0 to up to where 1, whatever the inputs here. In this case we have four input cases, four test. Okay, wait a minute. What happened? Right, in this case we have right. So in this case, we have all possible combinations 0 0 0 to all ones. So here we have four test inputs. Okay, we need to test four combinations here A, B, C, D. If we have suppose E, F, G, and you need to take E, F, G, all possible combinations. Okay, so simply, simply I'm saying here all possible inputs, test inputs, whatever, okay, provide provide CUT, next level, okay, that is circuit under test in BIST, okay. So simply exhaustive testing is nothing but whatever the input combinations we have, we need to consider all in this case, okay. So do not have any uh, uh, calculations taking four combinations or five combinations like that, okay. So all you need to take, right. Next is second one, uh, pseudo exhaustive pseudo exhaustive testing, okay. So in this I would like to take one example. So in this pseudo exhaustive testing we need to consider, if circuit is very big, we need to consider how many possible combinations we need to take. Input testing, right? So not combinations, input test, how many we need to consider, right? So in this case, for example, if I consider this is a AND gate, AND gate, AND gate, AND gate, okay. So this is X, Y. Any gates you need to consider here, not only I'm drawing this. I took this NAND gate here, okay. So sorry, 1 minute, right. So this is A, B, another value we have here in this case. Let us draw this complete, okay. And here it is, see one complex, not complex one, but this is C, and here it is connected. For example, like this, okay. One circuit I drawn here, okay. Now for this one, how to find, how to take combinations, how many combinations we need to test, okay, in this pseudo existing is, let us say the steps wise, roughly, briefly I will discuss here, okay. So step one, if I consider this is called generally dependence matrix, okay. So we need to generate a matrix generally called D, M comma and rows column, input and outputs, right. So for example, in this case I have uh, X and Y are the outputs, right. And what are the inputs we have? A, B and C, okay, right. Let us see ABC, what output X is depends on what values, ABC or AB or AC, let us see, okay. So this is X, so output of this, the input of this NOR gate, we have two, right, these two. So this is depends here, see, A and B, right. So I'm making this is high, right. Now this input here, here it is depends on this, so input of these two will be here, and this is here going whatever the buffer or whatever it is going, it is in depends on this, and it is again depends on a and b only, not c. So make it 0. What my point? Same here, y is, this is y output, right? NOR gate, and the inputs of these two are depends these two NAND gates, right? So it is depends on these two. So one is input is b, another one is c. So b high, c high. Let us this one I will check. Now in this is again we going for b, and this is going for c. Again c b. So it is not depends on a. Got my point? Just output depends on what are the inputs. Okay, we need to check primary inputs, right? Okay, now step 2 we'll see. Okay, so step 2 generally we will take partition. Now this above whatever the table we have, we need to partition this. Okay, so I can name it partition dependence matrix. Okay, then see here how to take the partition. XY are the outputs, and A, B. Now in this case, see, I'm writing directly. No need to take here B. See here, how we need to take this partition is nothing but, see, I have these values, right? Uh, A is 1, B is 1, C is 0. In this case, A is output of Y, A is 0, B, C is both are high, right? Now, how need to take means partition you need to make in such a way that one is high, another is low, one is high, another is low, or another is high, one is low, another is high, one is low, like that. Okay, that you need to consider partition. Okay, in this case, check, just check. See here, A is 1. Now this is low. 1 0. Now in this case 0 1, like this combinations we need to take. Both while taking partition, both should not be equal values, either 1 1 or 0 0, like that. Okay, so in this case what I would like to take C B, right? So let us see. So this is 1, A is 1 0, and this one is 0 1. Now this is as this 1 1. Okay, now this is a partition. Okay, so AC are they here partitioned, right? Now like that only we'll see the step 3. Okay, so one basic example I'm giving here. Okay, so practice yourself uh, while solving such a test. Okay, pseudo exhaustive test, right? Now step 3. Step 3 we need to reduce the pattern. So here is reduce partitioning, I can say. Okay, dependence matrix. Okay, so what we need to do here, reduce with the operation of OR gate, ORed. Okay, ORed value we need to take. So this is A comma C, and this is B. If I take these two, see how I'm taking. Now in this case A ORed B, you can say A, in this case A R B I'm writing. Okay, A R B, right? So A ORed B is what? If anyone is high, high only. So 1. Next is Y output, same, high. And this is also 1 1. Got my point? So reduced partition may be, you need to take OR the operation between partitioned one, which is A and C. So here is case, if I take ARC operation, so 1 1 will get, okay, XY outputs, right? So in this case, see, now we need to take another step. This is the last step, step 4, okay. Now we need to take a reduced verification. Reduced verification, okay. So consider P is equal to uh, number of columns, this table I am considering, okay, and W is equal to, we have number of ones, okay, in any row, okay, number of ones in any row, okay. So in this case, see, P is equal to, say, number of columns will be 2, number of rows in any column also 2, okay, number of rows in this 2, in this 2, okay, and rows, okay, this is columns. So in this case, P is equal to Z, sorry, P equal to W, okay. So how can we take this is considered as a 2 to the power of W, okay, which is nothing but 2 to the power of 2, it's nothing but 4 input tests we need to do. So in this case, I'm not going to go in depth. So 0 0 0 1 1 0 1 1, these are the 4, 1 2 3 4, 4 combinations we need to consider for the test. What my point? Okay, so this is the way of testing, okay. This is one of the method, uh, exhaustive, pseudo exhaustive testing, okay. One point. The last one we will see, third one. So brief idea only I am giving here, okay. So we'll provide notes for you, no problem. Random testing, okay. Third one is pseudo random testing. In this case, actually, uh, it is uses uh, linear feedback shift registers and flip-flops, okay. So here we are using flip-flops and linear feedback shift registers, okay. Generally we are using this testing, okay. So here we have two types of methods will be there, okay. One is internal XOR and another is external XOR, okay. So internal XOR, how to you calculate, okay. Suppose I have a characteristic equation, for example I have a, suppose x cube plus x plus 1, whatever the roughly I am taking here, okay. So for this one, what is test test pattern will be, okay. What is the test blocks we have, right? So in this case, x to the power of 3, so in this case we have x to the power of 3 here, right? X to the power of 3, then we need to consider 3 d flip flops. In this case I'm taking 1 2 and 3. This is d0, d1, d2, okay. Now we have linear feedback shift register, we need to take a feedback it is say, okay. Now in this case, second one is what is x only, x to the power of 1 is nothing but, so 1 we need to add here XOR operation at the input level, that's why it is named as internal XOR, okay. So this is generally called, modular LFSR, okay, linear feedback shift register. This is standard one, standard LFSR. Okay. So in this case, we need to add here one XR here. XR. Okay. Input level of D1. Why D1? So next term x to the power of 1. So at the input level, internal means input level. Okay. Now this is the select lines S0, S1, S2. Okay. So this is a design pattern of pseudo random testing. This is called random testing. XOR operation is nothing but indicates generally it's a random operation, right? So okay. Now in this case, for the same one, if I draw, it's simply reverse because external means from output level we need to take. So we have three flip flops, but the order will be D0, D1, D2. Okay. Again, consist of XOR operation. So okay, right. Then external means we have OR operation here. Okay, so in this case, sorry, XOR operation. This is XOR operation. So at this point of time, S0, S1, S2. Right? So in such a fashion, pseudo random testing is done. Okay. So this is the general patterns of pseudo random testing. Okay. See IDDQ testing. Okay. So what do you mean by IDDQ? IDDQ is nothing but direct drain quiescent current. Okay, so this is a full form of IDDQ, right? Let us see how this test will be done. See, sorry, when we have when VDD apply, for example, this is our circuit CMOS. This is output by now this is VDD and this is ground, right? So generally, what will happen? This IDDQ testing. See, when faults occur, various type of faults will be there. Okay, um, like VDD broken, source and ground drain broken, or gate broken, or line. I mean, inputs are floating, or outputs are shorted. Okay, so in such types, okay, we need this IDDQ testing will find such type of faults, right? So see here, when VDD applied to a CMOS chip, okay, then what will happen? Basically, the current IDD will flow like this, right? When it is happened, when the inputs are stable, okay, the quiescent leakage current, okay, this current, okay, I can say quiescent leakage current, that is nothing but IDDQ, okay, can be measured, right? This current can be measured if the chip is functioning properly only. See, remember, chip must be function proper only. Okay, right? So let us see what will happen. See, basically, suppose I have a fault in the gate or line. Okay, line means this is input, for example. Okay, and here I have a fault. okay, or in this is floating, for example. Okay, so in such a means there is no input here. Okay, in such times what will happen basically, see, the see this one ITD, what will happen generally, normal behavior of leak current and abnormal behavior we will see here. Okay, so this is suppose say Vmax, right? This is VDD here. Okay, this is V in, right? If I take here ITDQ, okay, so generally this will be flow like this. Suppose here somewhere very high and it will move like this. Okay, so generally this will be normal behavior. Okay, and this one is abnormal. Abnormal behavior. Okay, okay, so what will happen generally in such a large amount of flow of current will be there when the fault occurred in gate or floating input, then large large current flows. Okay, so see, good transistor, I mean good CMOS design will never flow large currents. Okay, when it consists of faults, okay, then it happens. Suppose my transistor is off presently, for example, so it should not be flow IDD here. Okay, so some fault with this transistor, okay, then CMOS, NMOS, PMOS, then automatically what will happen, this current will be starts flowing and there is a chances of huge leakage, right? So the here we are observing this leakage current, this is a normal value, and here see abnormal how much it is. Okay, so this is large amount it is flowing. Okay, so this is nothing but IDDQ testing. Basically IDDT testing, see here I will write few points here. So let us see, I will write few points here. These faults, uh, basically faults detected by IDDQ testing. Okay, so basic faults will be like bridging faults. Bridging faults already, you know what is the bridging faults. For example, if I have a circuit, I have a circuit, for example VDD, and I have a, and another circuit. This is, okay. For example, I'm taking this one. Okay, in such a fashion, what will happen? What will happen? This is ground. What will happen? Sometimes it consists this short of both. For example, if this is shorted, okay, so it's nothing but bridging. Okay, so IDDQ find this such type of faults also. Second one is, for example, not say, so many it is. As we discussed in the above, line and gate breaking, break faults. Okay, and the third one, so many. It is resistive. Actually, if you resist shots, then the fourth one, for example, drain source and drain breaking. Okay, break fault circuits. So such type of all faults, okay, you'll find by D IDDQ test. Okay, right. Next we will see. Next we will see scan based tests. Okay, let us see the scan based. Okay, so basically the scan based tests are operated in two modes. Okay, there are, I can say, two modes of, it consists of two modes of operations. Okay, the first one is normal mode and the second one is scan mode. Scan mode. Okay, so what do you mean by normal mode? Normal mode is nothing but they serve their basic functions. Okay, so generally normal mode in sense basic functions, whatever the basic functions the components have, it will perform the same. Okay, whereas the scan mode, okay, they are connected to a form like a what can you say, like a shift registers. Okay, it's a chain of shift registers basically. Okay, so okay, right, they are connected to form a bind shift registers. Okay, so basically these are called scan chain spanning. Okay, so basically these registers are called scan chain spanning the old chip. Okay, so how the structure, how they are performed. Okay, how they will test, let us see. Suppose this is the, so it consists of multiplexers. Okay, and we have four muxes. Okay, now this is what we have scanned input, and mux have selected lines, so I am naming it scan selection, and this is data data input. Okay, and it consists of flip-flops. Okay, now generally the flip-flops consist of clock, right, and the outputs are internally connected here, right. Now it is connected to cloud, Okay, so I can say this is a logic cloud, okay. Now this data is connected here, and this output is going to, so it will continue the same process. This is mux, okay. Again, it consists of selected lines, right? So inputs are connected like this. Okay, so like this, this is a single block of logic cloud. If we continue like this, it will extend it like this. Okay, again another logic cloud. Okay, so here this is a scanned input we have. Okay, this is a selection line. Okay, other, okay, this is a flip muxes are, this is a mux. Okay, now if selection line is selected, okay, then scanned input will be taken, otherwise it will take the data. Now flip-flops generally they consider this output of mux, and with the clock they will forward the whatever the data, either scanned one and this one. Okay, and here we will get the scanned output, scan output. Okay, so in such a fashion scanned based testing are performed, right? So these are the few testings, okay, we have in the syllabus. Okay, just go through it, and then you will understand better.